Welcome back to the deep dive. I want to start today with a question about your threshold for boredom. If I ask you to sit down and write, I will not talk in class 500 times, how long would you last?
Oh, wow. Maybe line 50. And even then, my handwriting would be terrible. I'd be skipping words. My hand would be cramping up. Humans are just not built for that kind of monotony.
Right. We crave novelty. We get bored. But computers, they are the complete opposite. You could tell a computer to print that sentence, what, 5 million times?
Yeah.
It would do it with a smile on its face, metaphorically, and never make a single typo.
It's true. It's one of the fundamental differences between, human nature and machine nature. We hate repetition. Computers thrive on it.
And that brings us to the stack of notes we're diving into today. We're looking at Chapter 5, Looping. It sounds simple, but reading through this, it really feels like this is the moment where coding stops being a calculator and starts being, well, actual automation.
That is a great way to put it. This is the turning point. Up until now, if you've been following the basics, code is pretty linear. You do step A, then step B, then step C. It's a straight line. But looping lets us bend that line into a circle. It's about harnessing that incredible stamina computers have to reduce redundancy, speed up development, and handle complex tasks without us having to hold the machine's hand the whole time.
Let's talk about that redundancy part first, because when I first looked at this, my immediate thought was, okay, if I need 5 lines of text, I'll just copy and paste the print command 5 times. It takes, what, 2 seconds? Why do I need a whole special logic structure for that?
That's a valid question. For 5 lines, sure, you can copy paste, but let's scale that up. What if you need to process 5,000 customer records?
Yeah.
Or 5 million?
Okay, right.
If you copy paste that code 5 million times, your program is going to be gigabytes in size before it even does anything.
Fair point.
But there's a more subtle danger too. It's all about maintenance. Let's say you copy pasted your code 10 times. Then your boss comes in and says, hey, we need to change the font size in that command.
Ugh. So now I have to find and fix it in 10 different places.
Exactly. And if you miss just one, you have a bug.
And if I had copied it 5,000 times, I'm basically looking for a needle in a haystack.
You've got it. So the core benefit of looping isn't just saving you from typing. It's what we call code redundancy reduction. You write the logic once. You tell the computer, here's the thing I want you to do. And then you say, do it 1,000 times.
So if you need to change it later, you change it in one spot.
One spot.
Yeah.
It's safer. It's cleaner.
It's working smarter, not harder.
I love that. So we have a few big objectives to cover from the source material today. We need to break down the anatomy of a loop because there are some strict rules here. We need to look at the different flavors, definite versus indefinite. And then we're going to get into some really trippy territory with nested loops.
Let's start with the structure, the definite loop. Now, when I hear definite, I assume that means we have a plan. We know where we're going.
That's it. A definite loop is for when you know exactly how many times you need to repeat an action before you even start. Think of it like a track race. You've signed up for the 1,600 meters. Before the gun even goes off, you're running exactly 4 laps.
Okay, so I'm on the track. I need to keep track of those laps so I don't just keep running forever. In the code, this is managed by something called a loop control variable.
Right. It's your counter. It's a little clicker in your hand. And for this to work without crashing your computer, you need to follow a mantra. 3 specific steps. Initialize, test, and update.
Initialize, test, update. Okay, let's walk through this slowly because it feels like if you mess this up, things go wrong fast.
You do. So step 1, initialize. This is just setting up your counter. You're at the starting line. In code, you'd usually set a variable, let's just call it I, to 0 or 1. You're establishing the starting point.
Okay, so I equals 1. I'm at the start.
Step 2, test. This happens before every single lap. The computer asks a question. Is I less than or equal to 4?
Well, since I just started, I is 1, so the answer is yes.
Correct, because the answer is yes or true. The computer runs the code, you run your lap. But then, and this is the step people always forget, you have step 3, update.
This is where I click the counter in my hand.
Yes, you have to change the variable. You add 1 to I, so now I becomes 2. Then the loop circles back to the test. Is 2 less than or equal to 4?
Still yes. Run the lap, update the counter to 3, test again, run lap, update to 4, test again, run lap, update to 5.
And here is the magic moment. The loop circles back. The test asks, is 5 less than or equal to 4?
No, that's false.
And the loop dies.
No.
instantly. The program just moves on to whatever code is next.
Yeah, what happens if I'm tired or just distracted and I write the code to run the lap, but I forget the update step? I never click the counter.
This is the classic rookie mistake. If you never add 1 to I, then I just stays 1 forever.
So it asks, is 1 less than 4?
Yes. Run the lap. Is 1 less than 4?
Yes. Run the lap. Oh no.
Is 1 less than 4? Yes. You're running until you die.
I'm stuck.
That is an infinite loop. The computer will literally do that forever until the system crashes or you force quit the program. It's the programming equivalent of Groundhog Day.
The source material uses a classic example for this, the 5 times table. Just a simple program that prints 5 times 1 is 5, 5 times 2 is 10, all the way up to 10.
It's the perfect example of a definite loop. You know the range is 1 to 10. You initialize at 1, you test against 10, you update by adding 1 each time. It doesn't matter if you're using Python or Java or C++ Westcut. The syntax might change slightly, like Python uses that for I in range.
Right.
But that core logic of initialize test update is universal.
So that's the definite side. It feels safe, it feels controlled, we know the destination, but, life isn't always that predictable. Sometimes we don't know how many laps we need to run.
Exactly. Sometimes you aren't running a 1,600-meter race.
Yeah.
Sometimes you're just running until you get tired or until it starts raining. You just don't know when that's going to happen.
This brings us to indefinite loops.
Right. And this is for when the number of iterations is unknown or it's determined by the user.
The source gives the example of a menu, or maybe a game. Like, the computer doesn't know if I want to play once, or 5 times, or 10 times. It has to wait for me to tell it to stop.
And that signal to stop is called a sentinel value. A sentinel is like a guard. It's watching for a specific signal. Common examples are things like typing -1 to stop a calculator, or typing Q to quit a program.
So instead of count to 10, the logic becomes keep going while the user hasn't typed Q.
Precisely. These are usually called while loops. But here's where it gets tricky. The logic flow is a bit different from the track race. The source material highlights a pattern called prime test prompt.
I found this part a little confusing in the notes. Priming the loop? It sounds like we're painting a wall. Why do we need to prime it?
Well, think of it this way. Imagine you want to ask your kids if they want pancakes. You can't just start cooking pancakes and then ask.
Okay, no. That would be a waste of pancakes.
Right. You have to ask before you even turn on the stove.
Okay, that makes sense.
That's priming. You have to get the first input outside the loop.
Yeah.
You ask, do you want pancakes? If they say no, the loop never even starts. You never cook a single one.
But if they say yes,
Then you enter the loop, you cook a pancake. That's the action. But then, and this is absolutely crucial, you have to prompt, again, inside the loop. You have to ask, do you want another pancake?
I see. If I don't ask again inside the loop,
Then you're stuck in the pancake version of the infinite loop.
oh no.
You asked once, they said yes, and now you are just flinging pancakes at them for eternity because you never gave them a chance to change their answer to no.
That is a hilarious and also terrifying image. So prime means ask once to get things started. Test checks the answer, and prompt asks again inside so we can eventually stop.
You've got it. And that prompt inside the loop is what updates the value for the next test. It's the number one thing students forget in while loops. They write the logic to process the data, but they forget to ask for the next piece of data.
So we've got definite loops for counting, indefinite for monitoring user input. But there was a small sidebar in the notes about post-test loops. We should probably touch on that.
Yeah, it's a variation. What we just described, checking about the pancakes before cooking, is a pre-test loop. You look before you leap.
And a post-test loop.
That's usually called a do-while loop. It executes the body of the loop at least once before it checks the condition. It's like eating a meal at a restaurant and then seeing if you have the money to pay for it. You're committed to doing the action at least one time.
That sounds risky.
It can be. That's why the notes emphasize that for most standard coding, especially with user input, the pretest loop with priming is the standard. It stops you from processing garbage data or doing something the user didn't actually want.
Speaking of processing data, let's look at why we actually use these things in the wild. We're not just printing times tables for fun. The source lists data validation as a huge application.
Well, this is massive. This is what keeps software from breaking. We call it defensive programming.
Defensive implies we're under attack.
You are. You're under attack from users who don't follow instructions. If you write a program that asks for a user's age and they type 25 spelled out or they type -50, that could crash your math logic later on.
So how does the loop help with that?
The loop acts like a bouncer at a club. You use a while loop. You just say, while the input is invalid, ask them again.
Okay.
So I ask for your age. You type -5. The loop checks it, sees it's invalid, and says, invalid entry, please enter a positive number.
And I type banana.
Loop checks. Invalid. Invalid entry, please enter a positive number.
Okay.
It traps you in that loop until you behave and give it valid data.
I have definitely been trapped in those loops on bad websites. It's annoying, but I guess it keeps the database clean.
Exactly. It ensures that once the code leaves that loop, the rest of the program can trust that the data is good.
Another application mentioned is the accumulator, which sounds very sci-fi, but looking at the logic, it's basically a digital shopping cart, right?
That's the perfect analogy. An accumulator is just a variable that keeps a running total. So you're writing a checkout program. You don't know how many items the user has, so you use a loop.
Right.
But before the loop starts, you have to create a variable, maybe call it total price, and you have to set it to 0.
Why 0? Why not just start adding?
Because you can't add apples to a cart that already has trash in it. You need a clean slate. You initialize the accumulator to 0.
Got it.
Then, inside the loop, user scans an item, it's $5. You add 5 to the total. Total is now 5. User scans the next item, it's $10. You add 10 to the total. Total is now 15. You just keep doing this.
And the loop ends when they hit the pay now button. That would be the sentinel value.
Exactly. And without that loop and accumulator combo, you'd have to write a program that only accepts a fixed number of items. Sorry, you can only buy exactly 3 things today. Just wouldn't work.
Okay, are you ready? Because now we have to go into the deep end. Section 5, nested loops. Loops inside of other loops.
This is where most people's brains start to hurt a little bit. It's that inception logic.
The visualization in the notes is a grid, but honestly, even looking at the diagram is hard to picture the flow. You have an outer loop and an inner loop. How do they talk to each other?
The best way to visualize this isn't a computer screen. It's an analog clock. Picture a clock with a minute hand and a second hand.
Okay, I'm picturing it.
The minute hand is your outer loop. The second hand is your inner loop.
Okay.
Now think about what has to happen for the minute hand to move just 1 notch.
The second hand has to go all the way around.
All the way around. Tick, tick, tick. 60 times. The inner loop, the seconds, does a complete cycle, start to finish, for every single step of the outer loop.
That actually makes it click for me. So if the outer loop runs 3 times and the inner loop runs 10 times.
Then the code inside that inner loop runs 30 times total. 10 for the first adder lap, 10 for the second, and 10 for the third.
The source material uses a coordinate example, like a 4x4 grid. So we have rows and columns. Let's say the outer loop controls the rows from 0 to 3, and the inner loop controls the columns 0 to 3.
Right, so the system starts. Outer loop, row is 0, it pauses, it hands control over to the inner loop. The inner loop wakes up, it says, okay, I need to print columns 0, 1, 2, and 3. So it prints 0, 0, 1, 0, 2, 0, 3. Then the inner loop finishes. It's done its job.
And only then does the outer loop wake up again?
Yes. The outer loop says, great job, now I'm moving to row 1. And here's the catch. The inner loop restarts from the very beginning. It doesn't pick up where it left off. It resets to 0. So now it prints 1, 0, 11, 1. Oh, no, 1, 3.
So the inner loop lives a full life, dies, and is reborn every single time the outer loop takes one step.
That's a very poetic way to put it. But yes, that's it. And this is how we build grids, spreadsheets, images on a screen. Pixels are just rows and columns controlled by nested loops.
The notes have a specific key practice warning here. Debug the inner loop independently first.
So absolutely. If you try to write the whole complex clock at once and it's not working, you won't know if the problem is the minute hand or the second hand.
You're lost.
Totally. So you write the code to print one row correctly. Get that working perfectly. Only then should you wrap it inside the outer loop to repeat it. Build the engine before you try to drive the car.
That seems to be the recurring theme today. Structure. Whether it's the initialize test update of the definite loop or the prime test prompt of the indefinite loop or this clockwork logic of the nested loop, you can't just wing it.
No, you can't. The computer is a powerful servant, but it's a very literal one. It will do exactly what you tell it to do. You tell it to loop forever, it will. If you tell it to skip a prompt, it will. The logic has to be airtight.
So if we zoom out, what's the big takeaway for someone listening who might not be a coder but just wants to understand how this tech works?
The takeaway is that automation is just managed repetition. Everything you see a computer do, streaming this, checking your bank balance, rendering a video game, it's all just a series of loops, checking conditions and updating variables millions of times a second.
It changes how you look at the world. You start seeing loops everywhere. Actually, the source material gives us a little homework challenge, and I think it's a fun one to try mentally. It asks you to convert a repetitive, everyday task into pseudocode.
I love these thought experiments.
hmm
The examples they give are things like checking a shopping list or entering a PIN number.
As I was reading that, I realized I run a loop every single time I leave my house. I tap my pockets.
Mm,
Prime, tap pockets, test. Do I have keys, phone, and wallet? If I know, loop body. Go find the missing item.
right.
Update. Tap pockets again. Test. Do I have them now? If yes, exit loop and leave the house.
That is a perfect while loop. And notice, you have a sentinel condition, all
Yeah.
3 items present. If you never find your wallet, you are stuck in your house forever.
An infinite loop.
Hmm.
That has definitely happened to me. So to wrap this up, I want to leave you with a thought about that exit condition.
Hmm.
In programming, every loop must have a clear way out, a sentinel value, a limit. If you think about your own habits, your own loops, do you have a clear exit condition?
That's deep. Are you scrolling social media in an infinite loop because you forgot to set a sentinel value like turn off at 10 p.m.?
Exactly. Sometimes we need to debug our own operating systems. Thank you for going on this loop with us today. We hope you didn't find it too repetitive.
I see what you did there.
We'll see you on the next deep dive.